Hello everyone, welcome to lecture 24 of the online course Modern Display Technologies Flat Panel Display. Today's lecture will be discussing the multi-domain vertical alignment and the optically compensated band, that is OCB mode. So here's the lecture outline. The lecture has three parts. First, the multi-domain vertical alignment, MVA, the motivation for splitting each pixel into 4 different domains and the resulting viewing angle physics will be discussed. Second, we will talk about the wide view compensation films for MVA LCDs that are used to further widen the MVA's contrast cone, designed using the point care sphere graphical method. Both a 2-film and a 3-film version we'll see. And third, we'll discuss about the optically compensated band OCB mode. Okay, the pi cell mode, its first switching band geometry and its own discotic compensation film requirements will be discussed. So let's start our discussion with why a single domain vertical alignment is not enough. We have seen in the previous lecture that the vertical alignment is the best contrast ratio liquid crystal mode with speed traced to the band elastic constant K33 and a full closed form treatment of the switching dynamics plus the overdrive, undershoot, drive tricks. All these things we have already understood. Now the weakness we have seen is that the single domain vertical alignment cells, their viewing angle is narrow and asymmetric for the direct view use, because the vertical alignment liquid crystal layer acts like uniaxial C plate for obliquely incident light, and the cross polarizer geometry stops being ideal off axis. Okay, so single domain vertical alignment is good for liquid crystal on silicon or say projection type small displays where the eye views only along one fixed axis. The problems come for the direct view TVs and the monitors, okay, for the off axis viewing where the crossed polarizer dark state degrades sharply at large oblique incidence. So what is the discussion or the way out of it was that the single domain vertical alignment, the main weakness of that is the narrow and asymmetric viewing angle. So the first thing, we can actually split that pixel into multiple domains, okay, and that is your concept of multi-domain vertical alignment, and so that will solve one problem of widening the viewing angle. And for different first switching architecture, okay, that can also be solved using the optically compensated band pi cell, that is the OCB cell. Okay, so in today's lecture there are basically two major parts. First, the multi-domain vertical alignment, we'll discuss that, which basically fixes the viewing angle problem by splitting each pixel into multiple domain, plus then we will discuss the compensation film schemes which are used to further widen the contrast cone. Okay, and then secondly we'll talk about this first switching architecture. Okay, this is a completely different first switching liquid crystal mode called the optically compensated band pi cell. So this slide discusses the core structural idea of the multi-domain vertical alignment and its main commercial variants. Okay, so here you can see the 4-domain multiple domain vertical alignment or MVA structure and the transmittance curve. Okay, so this is generalizing the 2-domain chevron idea, which split each cell into 4 domains, each with a different LC pre-tilt or azimuth direction, right, as you can basically see here. These are the 4 domains. Okay, and these are the absorption axis of the polarizer and this is the absorption axis of the analyzer. Okay, so these are basically the 4-domain liquid crystal director. Okay, one is up, one is down, one is right, and one towards left. So what is happening here is that if you consider the two dominant commercial implementation, one is the Fujitsu's protrusion type MVA, and which uses physical bumps on the substrate to basically pre-tilt the domain, and then you have Samsung's patterned vertical alignment or PVA, which basically uses patterned slits in the electrode to create fringing fields that basically set the domain direction without any physical protrusion. Okay, so this method PVA can provide higher contrast ratio since the light scattering protrusion structures are not present. Okay, wherever there will be this kind of protrusion structure, there will be leakage. Okay, so what we understood, that PVA method, the Samsung's method, requires no physical protrusion, so you can get higher contrast ratio out of it than the protrusion type MVA, which is proposed by Fujitsu. So this particular figure here, we have already discussed the 4-domain liquid crystal diameter distribution in the voltage on state, right? Here you can see the voltage dependent transmittance curve of this multi-domain vertical alignment LCD, and these are blue, green and red. Okay, and you have already seen similar kind of graph before. So this is the simulated VT curve, and one close match is that this looks very much similar to the one we have seen for the single domain. So if you average the multi-domain, you will get the similar kind of performance. Now let us see how the problem of the viewing angle can be solved. Now first of all, why 4 domains are not alone sufficient to solve this, that you can see from this particular slide. Here it shows that the 4 domains alone are not enough. The simulated ISO contrast contour, okay, is shown without any compensation film. So even with the 4 domains, the ISO contrast contour without the compensation film provides still poor bisector viewing direction, particularly at 0 degree, 90 degree, 180 and 270 degree. Okay, so at this bisectors, 10:1 contrast ratio contour only extends up to say 30 degree polar angle. Okay, so that is not good. So you can basically particularly see this azimuths, okay, and the 10:1 contrast ratio only reaches about 30 degrees of the polar angle. Okay, you can see here, yeah, this is the 30 degrees, yeah, it's here. Okay, so only up to 30 degree you can get that 10:1 ratio. After that, for higher, the contrast ratio is going down very fast. So what is the physical origin of this? So explaining the 2 physical causes carefully. Okay, since this sets up the composition film design work that is going to follow. The first one is that at oblique viewing angles, the projected absorption axis of the cross polarizers are no longer exactly perpendicular to each other, right? So that basically degrades the dark state. The second is that the vertical alignment layer basically behaves as a C plate or uniaxial C plate that imposes physical or phase retardation on obliquely incident angle. Okay, so what exactly happens there is that the vertical alignment liquid crystal itself acts like uniaxial C plates for obliquely incident light, and it imposes an unwanted phase retardation that basically further degrades the contrast. So this basically sets up the tone that why we need the compensation films specifically designed to cancel both of these effects simultaneously. Okay, so here we'll first see the unwanted phase retardation, that is gamma LC, which is introduced by the vertical alignment liquid crystal layer at oblique incidence theta naught. So this is the expression, okay, for this MVA liquid crystal layer. So this is the phase retardation, the quantity every compensation film skin will be targeting to basically cancel out. Now what you see here is that there are the ordinary and the extraordinary refractive index values getting in, okay, and then this is the thickness layer of the liquid crystal, and theta naught is basically giving you the incident of the viewing angle. So for a viewer looking in at the incident angle theta naught, the vertically aligned liquid crystal layer basically behaves like a uniaxial C plate. You have this NLCE and NLCO, so it's like a uniaxial C plate, and it also gives you a phase retardation, that is that gamma LC, okay, this capital gamma LC, that basically depends on the liquid crystal's extraordinary and ordinary refractive indices, as well as the thickness of this liquid crystal layer and the incident angle itself, right? Now if you take an example at a design incidence angle of 70 degree, okay, you will see that this is the parameter for mainly MLC 6608 material, okay. So the phase retardation comes out, gamma LC comes out to be around 0.664 pi radians. So this is the retardation every compensation film scheme must target to cancel out. So you can see the parameters involved here. So this is the cell gap, this is the surface pre-tilt, this is NE and NO. You can basically see the birefringence here, and then this is phi 1 and phi 2. These are the absorption axis of the polarizers, okay. So they are 90 degree apart, and the lambda is considered to be the green one, 550. So let's see the compensation film designs. So the first one is basically a positive A and a negative C film, okay. So how it works, you can see here. So this is the first and the simplest wide view compensation architecture for multi-domain vertical alignment, where one positive A film plus one positive C film is used. So you can see this particular figure. So this is the divide structure of a MVA LCD using a positive film A film and a negative C film. So you have the polarizer absorption axis at 45 degree, you have a positive A film with optical axis at minus 45 degree, and then you have a negative C film, and then you have this MVA LC layer, that is the 4 domain one, and then you finally have the analyzer absorption axis, which is also at minus 48 degree. So how it is designed, you are seeing that first you have a polarizer, then you have a positive A film with its optical axis basically parallel to the analyzer's absorption axis, and then you put a negative C film, and then you are bringing the LC multi-domain vertical alignment liquid crystal layer, and then the analyzer itself. So here the state of the design, the objective is to that we want to choose the thickness and hence the phase retardation of each film such that at 0 volt the observer looking in from an oblique bisector viewing direction still sees a fully absorbed black state exactly as they would have seen it on axis, okay. So that is the main goal, so that V equals 0 from any oblique incidence also it should look like a very good dark state, okay. And this design method basically uses the Poincare sphere. So this is basically a graphical tool that can be used to actually solve for those thicknesses, okay. So we'll see that in details here. So this is the slide that shows you the Poincare sphere compensation mechanism conceptually that will allow you to design that kind of compensation film, okay. So the unpolarized light basically passes the polarizer, okay, and the linear polarization state, the way it works is that you need to first trace the polarization path step by step. Okay, so unpolarized backlight becomes linearly polarized light from the polarizer. Okay, because the backlight passes the polarizer, it gets the linear polarization. Okay, and landing at point T on the sphere. Okay, so this is where it lands at point T, which viewed obliquely, okay, is actually rotated away from the analyzer's own point A. So this is the analyzer's point A, but it is basically rotated away. Now if you have a positive A film, that basically rotates the state clockwise around its own axis. So from T to a first intermediate elliptical state E. Okay, so it first goes here. Okay, then the negative C film rotates the state counterclockwise around a different axis, arriving at the second intermediate state, that is F. Okay, now passing the unactivated multi-domain vertical alignment liquid crystal layer, which also acts like a C plate for this particular oblique ray, it will also rotate the state clockwise one more time. So from F all the way back to A. Okay, that means the light is now fully absorbed by the analyzer. So you are getting a good dark state, and this is restored even for the oblique bisector viewing direction. So what you have seen here, so you are basically using three geometric condition, equal arcs, equal angles on this path. Okay, that yield the closed form film thickness equations. Okay, and the actual film thicknesses are found by imposing three geometric requirements on this particular path, that equal arc and equal spherical angle, which is basically the spherical trigonometry. So you are not using the calculus. So this is how you can basically understand the compensation principle of an MVA LCD using a positive film and a negative film. Now the film thickness design equations we can see here. The spherical trigonometry conditions give the required angles, which are basically angle EAC. Okay, so that comes out to be cos inverse of minus C T G square phi, and then angle is, that is ACE. Okay, which is 2 sin inverse CT G phi, and then you can find out the positive A and the negative C film thickness. So you can call DA plus, as you can calculate it from this equation. Okay, so these things are coming directly from the spherical trigonometry conditions on the point K sphere path that is traced on the previous slide. We have seen that they give two spherical angles that fix how much each film needs to rotate the polarization state. So you are getting DA plus and DC minus, that's the thickness of the positive and the negative C film. So these thicknesses are basically giving you the physical film thickness of this kind of films. Okay, that are using the standard phase retardation to thickness relationship for a uniaxial film at oblique incidence. And the similar kind of expression was also used earlier in the gamma LC. Now emphasizing on the design input, you can see here is that everything depends only on the effective polarizer angle phi, the incident angle, that is theta naught. Okay, and the ordinary and the extraordinary refractive indices of the two films. Okay, so you can always get it from the standard catalog data for any commercial retarder films. Okay, so phi is basically the effective polarizer angle on the wave plane, okay, from the low bisector viewing position. Now when you solve for this design angle theta naught equals 70 degree, you want to see what will be your dA plus and DC minus, they comes out to be this. Okay, now with these films, the bisector viewing angle, so you can again put them here, okay, on 0 degree, 90 degree, 120, 180 and 270 degree, you can see that they have dramatically improved the contrast at larger angles. So even at say between this is 30, 40, 50, 60 degree angle also you are getting more than 1000 contrast ratio. Okay, and while the on axis contrasts like 48 degree, 135, 225 and 3115, they remains same. Okay, so these are very good improvements, but one limitation is that the 100:1 contrast ratio still this is the ISO control only still reaches 75 degree polar angle, that is somewhere here, yeah, that's 75 degree. Okay, it's not as good as the IPS because the immediate intermediate states which you have seen E and F, they don't lie on the sphere's S1 S2 grid cycle, so they don't have the same kind of benefit. Okay, this, so but still this is particularly very good. Now let us see the second scheme which tries to improve upon that. Okay, so here is an improved architecture that adds a second A film. So you are now adding another A film, positive A film, that sits between the polarizer. So this is a positive A film, and then you basically have the A film sitting between the polarizer and the liquid crystal layer. So it's here, okay, liquid crystal layer and the polarizer, that's the positive A film, and then you have a negative A film and negative C film between this the liquid crystal layer and the analyzer. Okay, now what is the intent of this design? You want to basically force the intermediate polarization states E onto the sphere's S2 S3 grid circle that will be bisecting the arc. Okay, so that will basically try to fix the problem of that scheme 1. Okay, so what is the path that should be followed now? So you can go back and see that particular circle. So you basically want to go from T to E via the positive A film, and then you go to F via the liquid crystal layer, and then you come back to E again via the negative C film, and then finally to A via the negative A film. So here the geometric condition is that the triangle ETA basically becomes a equilateral spherical triangle. Okay, it's a equilateral spherical triangle. So when you have this equilateral triangle condition, that gives the shared spherical angle and also the three film thicknesses, that is dA plus, dA minus and DC minus. Okay, so you can obtain these angles like angle EAT will be equal to angle ETA, which is equal to cos inverse of minus CTG phi dot CTG 2 phi. So you can basically obtain, these are the equations that gives you the values of this film thicknesses. So they are basically they are converting the shared angles plus the liquid crystal retardation into 3 physical film thicknesses that is required to specify this particular scheme. So as with all these 3 thicknesses, as you can see, they depend on the incident angle theta naught, the relevant film refractive indices. Okay, or everywhere you have this extraordinary and ordinary refractive indices, and the gamma LC. So that is the same design of similar to the scheme 1, just that now you are solving for 3 unknowns other than 2. So if you go back to that angle of 70 degree and you solve it for these 3 thicknesses, you get these particular values, and with that if you plot your iso contrast contour, iso contrast means so the contrast remains same on that contour. So if you do that, the bisector direction contrast again dramatically improved. So you can see here the contrast ratio is now very high. Okay. However, the on axis contrast, like along the 48 degrees and 135 degrees, they remain unchanged. So it's a qualitative win over scheme 1. However, the remaining limitations here is that even though in this case E and F are made to lie on that S2 S3 great circle, you can see here that great circle we are talking about. Yeah, this is that S2 and S3 great circle. Okay, there are the 3 axes. Yeah, they are not symmetric about the equator. Okay, and that's why you'll see that the 100 contrast ratio still stops around 75 degree polar angle, right? So this is the polar angle till 75. I think you are getting that 100:1 ratio. Now, so what do you understand here? The final thing is that we need to look into some other schemes. Okay, so let us focus on this another mode, which is that optically compensated band mode or OCB mode. So the core structural element here is the pi cell. Unlike a standard pneumatic cell, the pre-tilt angle at the 2 alignment surfaces points in opposite directions rather than in the same direction. Okay, so this is why the OCB cell is. Okay, so it is basically it uses a voltage biased pi cell. So at 0 voltage, the director configuration is in a splay state, and once you apply the voltage that is above the critical voltage VC, which is roughly around 1 to 1.5 volt, the cell basically switches to a band state. Okay, the operating state that is basically used for the OCB displays, right, the band state. So here the opposite pre-tilt basically gives you 2 properties. The first one is inherently symmetric viewing angle, and the band director profile eliminates the backflow effect, so you get very fast response. And because of the on axis contrast ratio is still low from residual retardation, so this optically compensated band also requires us optical compensation films, that those are the discotic materials. So in summary, for this particular technology, if you want to highlight the first 2 payoffs of the opposite pre-tilt band geometry, the first one is that the viewing angle becomes intrinsically symmetric because the retardation stays nearly constant as the incident angle changes within the director plane. And the second one is that, as just important, okay, as the first one, the band direction profile basically eliminates the backflow effect that slows down other LC modes. Okay, so here there is no conflict between the flow induced torque and the director's own relaxation torque, so that gives OCB very fast response time. Now only one weakness that remains here, as I mentioned, the on axis contrast ratio is still relatively low because of the residual retardation in the pi cell even at high applied voltage. So real OCB panels still need to be dedicated optical compensation film, okay, which we'll be seeing now. So these are the voltage dependence transmittance curve of a pi cell. Okay, here we consider d delta n to be 436 nanometer, delta epsilon as 10, and uniaxial film thickness d delta n to be 53.3 nanometer with a pre-tilt of 7 degree. So what you see, this is the transmittance versus the voltage graph. A common dark state is there for all RGB wavelengths that appear around 4.5 volt. Okay, and the wavelength dispersion here is a concern for any birefringence display. So that is fixed here by using slightly different cell gaps per color subpixel, something like you use d equal 6 micron for the green and 7.1 micron for red and 4.9 micron for blue. So you can actually take care of the wavelength dispersion that way. So the switching time between the gray levels is typically less than 3 micron. So this is one of the fastest among the all liquid crystal modes, and it is important for cold ambient LCD TV usage. Now, why this OCB is fast and what's the need of the compensation film? So the three factors give OCB its fast response. The first thing is the bias voltage, that is a surface mode effect, the flow effect that we have discussed, and the half cell switching. So unlike the twisted nematic, multiple domain vertical alignment and the in-plane switching mode, these pi cells have no conflict between the flow induced torque and the detector's relaxation torque. So the backflow does not actually slow it down. Now to reach a high on-axis contrast ratio and match the vertical alignment and IPS level wide viewing angle, OCB needs a discotic, that is like polymer discotic material or PDM, okay, compensation film, which is developed by the Fuji photofilms. So this PDMs, what they do, they has a hybrid alignment mimicking the half the pi cell's own band structure. So its azimuthal alignment sits at 48 degree to the polarizer's transmission axis. So here you can see the simulated isocontrast contour of the Fujifilm compensated OCB. So that's the blue one is like 10 and the red ones are like 100. So here you can see very high contrast in all those directions. So with this OCBs with compensation, the viewing angle becomes comparable to the vertical alignment and the IPS, plus less color shift at intermediate gray levels. So in this case the human skin tones look good even off axis. So to summarize, we'll compare this with the LC modes. So MVA, the 4-domain generalization of the chevron idea. We have seen they have got wide view compensation films based on the point care design that can push the contrast ratio 100:1 to 75 degree, that is close to, still not quite matching the IPS in-plane switching kind of performance. Then we have seen the OCB pi cell, they give fastest response of the modes studied, so less than 3 millisecond response time. Backflow free band geometry, but they require discotic compensation film for compensating the viewing angle and the contrast. And then we have seen the vertical alignment family. We discussed about the single domain, why you need to move to the multiple domain, and then compare them with the IPS and the twisted nematic. And finally we understood that the VA and the multiple domain VA, they wins on the contrast ratio and the speed. However, IPS remains the wide view benchmark because the contrast ratio is very high on the wide angle oblique angle view, and the twisted nematic basically requires d delta n budget. However, it is the simplest and the cheapest one. So recurring design pattern across this whole module. So you can split a pixel into domains. You can use it for chevron IPS or 4-domain MBA, or after that you can add compensation film for AMBA or OCB, this can trade the manufacturing complexity for the optical performance that you require for your display. So with that, we conclude this lecture. If you have got any doubt regarding this lecture, drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.